This one is 2.31. Here we have a composite hoop that is made of two hoops, one made of brass, one made of steel. The dimensions are given here. Brass is internal radius 300 millimeter and thickness 3 millimeter. Similarly, your steel is 303 millimeter internal radius and 6 mm thickness there. Now this assembly has this internal pressure which is 1.4 megapascals, and we need to figure out what is the tangential force in these individual hoops there. Now for this purpose we can recall example 2.7, where if there is a hoop which has internal pressure P here, we can look at in a small section here and relate this tangential force by doing a force balance on this. So if I take this small area, so the force on this is going to be PdA, and this Ft will be balanced by the vertical force there. So PdA, if this angle is theta, sin theta component, this will be integrated and it should be balanced by Ft. Now your dA can be written in terms of outer plane thickness B times this arc length, which is going to be r d theta times sin theta, equals to 2 Ft. If I simplify this, I get Ft equals to P times r times B. So a tangential force for a hoop with internal pressure P, radius r, and outer plane width here is given as B, is given by this formula. Now let's look at this problem. Let's isolate these two separately. So if I look at the inner hoop, and this one is your outer hoop. So this one is inner, which is made of brass, and this one is your outer one, which is made of steel. Okay. Now on the inner hoop we have this pressure that is given to us already, which is 1.4 megapascals. Now since this inner hoop is in contact with steel from the outside, there will be this pressure that comes from the steel hoop on it. And what is the value of this? We do not know, so let's keep this as a question mark. Now the radius of this hoop right here, we can take a mean radius. The inner radius is 300 and the outer one is 303. So one radius for this we can write it as average of these two, which is 301.5 millimeters. Now on this we are going to have these tangential forces. So let's call this FB and FB here. Now outside the plane on this dimension here, this is B, which is given as 6 mm in this case. So writing down your FB based on this relationship that we have written, it's going to be 1.4 megapascals times RB times B. Now this is on the positive side. Now if you notice, there is a negative pressure also, which is P. So this will be combined with P pressure times RB times B. So for this hoop, we can write your FB is 1.4 minus P times RB times B. This is the first equation we have got. Now looking at the outer hoop, now this pressure which was acting this way on the inner hoop, it's going to be acting as an internal pressure for the outer hoop in this manner, and this value is P. Now for the tangential forces here, we can take this as Fs for steel. Now radius in this case from here to here, Rs, we can take an average. So inner one is 303 and the outer one here is 309. So an average is going to be 306 mm here. So in this case, your Fs can be written as P times Rs times B. This is our second relationship. Now if you look at number of unknowns here, your Fs is an unknown, P is an unknown, and Fb is an unknown. So again we have three unknowns and only two equations. So we need to have one relationship which is coming from your deformation, meaning this contact here where your brass and steel hoops are matching, their deformation should also come out as same, otherwise they will lose contact. Now how do we write these deformations? You can write them in terms of FB over EB AB, which is your Hooke's law. Similarly FS LS over ES and AS. Now what are these numbers? Your LB for the half hoop, we can write it as pi RB. LS can be written as pi RS. We already know the value of RB and RS. Now EB, which is for brass, we can take 103 GPa, and for steel we can take 205 GPa. Now cross section area AB. What is this cross section? This cross section is basically, if I go somewhere here and try to see this part, right? So outside the plane we have B, and this thickness will also come into picture, right? So thickness for brass is 3, thickness for steel is 6 mm, and both of them will be multiplied by that out of plane thickness. So your area for brass is going to be 3 mm thickness times 6 mm outside the plane, and similarly for steel it's going to be 6 mm thickness and 6 mm outside the plane. So now we have everything here. So we can discard this and we can take this as third equation, because now we have relationship in terms of FB, FS and P. So if I solve these three equations, I get the value of P as 1.11 megapascals, value of FB as 520.6 newtons, and value of Fs as 2042 newtons. Now once this is known, we can go back to these formulas and we can find the value of delta B equals to delta S. And remember, these relationships were written for half hoop. Okay, so for the complete hoop we can write down your delta S 2 times delta B. So in terms of change in perimeter, your perimeter change is going to be 2 times delta B, which comes out as 0.53 millimeters. And if we are looking for change in radius, your half hoop, which is pi times RB, we can take this value and divide it by pi, so 0.53 divided by pi, and this gives you delta RB, which is 0.084 millimeters. So these forces were asked in problem number 2.31, and this change in radius and deformation, these were asked in problem 2.32.